We've reached week 5 now, so let's do a preview of the major topics of the week. We've labeled it Space-Time Switches. There are actually a number of different topics we're covering, but the idea of space-time switches comes from the Lorentz transformation, which we'll be talking about. It enables us to switch between different frames of reference very easily. But before that, we'll have the quotations of the week. We'll do that in a minute. We'll talk just briefly about convenient units for the speed of light, the concept of a light year, and the fact that if we measure distances in light years, a light year is a distance. The distance light travels in a year, as some of you may know. If we measure velocities in light years per year, then c, the speed of light, is simply 1. By definition, it's 1 light year per year. It's the distance it travels in 1 year. And so that, and a couple of tips there will make things a little easier for us calculationally when we do things. And then we're going to spend a little time looking at a case of time dilation and length contraction to build on the ideas we were working with last week. We introduced and derived last week to get some more familiarity with them, to struggle with them a little bit, try to get a deeper understanding of it. And we're calling this Star Tours Part 1. The idea is we're going to send, in this case, Bob will go on a trip to a nearby star, 5 light years away. The nearest star to Earth actually is about 4.2 light years away. We mentioned that in one of the early problem sets. But I think we mentioned in terms of the distance, not in light years, but just in how long light would take to get there. It's about 4.1, 4.2 years. Anyway, so we're just going to imagine Bob taking a trip there, and we're going to analyze it from Alice's perspective as she watches Bob take the trip to the nearby star, and she's on Earth. So we'll analyze it from her perspective and Bob's perspective. We'll try to make sense of both their perspectives, and then we'll sort of hit a wall, hit a puzzle in that there'll be something that really doesn't make sense we'll get to. And so we'll have to hold that aside for a minute, and because we won't be able to answer it yet. And that's really what the next part here is. In order to answer it, we're going to derive the Lorentz transformation. The Lorentz transformation, just like the Galilean transformation, allowed us to switch between different frames of reference in a non-relativistic manner. The Lorentz transformation, also derived by Einstein, but typically called the Lorentz transformation now, allows us to switch between different frames of reference when relativistic speeds are involved. And it actually is equivalent to the Galilean transformation for slow speeds. So it subsumes the Galilean transformation. So this will probably be the most algebra we do in the entire course. It will take us a while to get through it, several video lectures, but we'll work our way through it and then get these transformation equations. And then we'll spend a little time exploring those transformation equations, trying to understand them, seeing what they're telling us, see if they make sense from what we know so far. And then we're going to use those transformation equations. They're very general, useful in all kinds of ways, but we're going to use them to revisit this whole idea of leading clock's lag, because this will turn out to be the key to understanding our Star Tours conundrum that we end up with there. So we're going to revisit leading clock's lag and do it quantitatively. Find out exactly how much do leading clocks lag. Remember when you have a series of clocks moving by you, you're in one frame of reference, you see 2 or more clocks moving in another frame of reference past you, then the leading clock, as it's moving past you in that series of clocks, or 2 clocks, lags behind the rear clock. And we did that qualitatively before. Now we'd like to figure out exactly how much does it lag behind that clock, and that's going to be the key as we discover to figure out this problem we run into. So that's Star Tours Part 2 here. And then we'll say a few words about the ultimate speed limit, speed of light being an ultimate speed limit, and why that might be so, what would happen if you could travel at the speed of light. And then finally, talk about combining velocities. We did a little bit of this with sort of the Galilean transformation idea, where if you have a car and you have a basketball shooting machine that we talked about, and then a tennis ball out of the basketball, that type of thing. In our everyday experience, those types of things just add. You add the velocities, or if the velocities are opposite to each other, you subtract the velocities. Well, a similar idea in terms of the special theory of relativity, but it's a little more complicated. Because if the speed of light is an ultimate speed limit, what if you have something traveling at 0.9 c, say Bob on his spaceship traveling at 0.9 c, and then he shoots out maybe an escape pod or something, traveling at 0.5 c away from him. So he's traveling at 0.9 c, 9/10 the speed of light. He shoots out an escape pod at 0.5 c, so that's 0.5 c with respect to him traveling away. In sort of classical physics, we'd say, oh, you just add the velocities. It's 0.9 c plus 0.5 c. Alice, watching it over here, as Bob goes by and shoots off the escape pod, Alice would say, presumably, 0.9 c plus 0.5 c, 1.4 c is the velocity of the escape pod as she sees it. But in actual fact, you will never see anything go past the speed of light. And so combining velocities here will show us the new formula for doing that, such that no matter how fast Bob shoots out that space pod or whatever, Alice will never see it go faster than the speed of light. Actually, will never get up to the speed of light, but it will never exceed the speed of light there. Okay, so that's sort of a rundown of where we're heading this week. Let's do the quotations of the week. 2 short ones this time. First one, Einstein. It's not that I'm so smart, it's just that I stay with problems longer. It's not that I'm so smart, it's just that I stay with problems longer. Now, I said Einstein, quotation from Einstein. In actual fact, Einstein probably did not say this. It's one of those things that somebody invented at some point, and it sounds good. It sounds like Einstein could have said it. It's certainly inspirational, and therefore you see it all over the place. In actual fact, it's something he could have said, because he certainly did stay with problems longer. He certainly was very, very smart. Hard to measure those types of things at a certain level, but great scientists also had this tenacity about them, and he was tenacious when he got onto a problem. We saw that in the special theory of relativity. It was about 10 years of thinking about that, other things as well, but 10 years from about 1995, 1996, when he started in the university, to year 1905, I should have said 1896 if I said 1996, to 1905, 10 years. And then actually the next 10 years after that, he spent a large part of time working on his general theory of relativity. It took about 10 years to work on that, as well as a number of other things as well. So that tenacity, that idea that I'm going to stay with this problem. Now, it's not always a benefit, because if you go off in the wrong direction, you may be going off in the wrong direction for a long time. And in fact, many physicists who are contemporaries of Einstein during the second half of his life felt that he had gone off in the wrong direction in terms of the physics of the day, which had gone in much more quantum mechanical direction. And Einstein had some real problems with that. And so really for the last half of his life, from about 1925 on or so, he was out of the mainstream of physics. He's certainly revered by many people and physicists, but just did not really contribute anything major at the time from about 1925 to he died in the 1950s. So again, it's a good quality to have, no matter how smart you are, however you want to measure that, but that just staying with the problem longer, that struggle for understanding we've talked about before. So even though Einstein probably didn't say it, it certainly captures one aspect of his scientific personality. And the second quotation, similar to the first, and this one is something he said, one should not pursue goals that are easily achieved. One must develop an instinct for what one can just barely achieve through one's greatest efforts. And so there's that insight into you want to tackle problems that are challenging for you, but you also have to have some insight sometimes, is this just too hard a problem? And scientists have to have that as well. They have to understand, given our current capabilities, our current understanding, my current abilities maybe, that's just something, it's not good for me to tackle. Leave it to somebody else, or leave it for 20 years from now, and maybe we'll be able to come back and tackle that problem again. On the other hand, sometimes the really hard problems like that, the only way you really do crack those nuts, as it were, is for somebody to take it on, or a group of people really to take it on and to stay with that problem until it gets solved. Okay, so that's overview of the week, where we're heading, quotations of the week, and again, we're going to be building on the things we've been doing the last couple weeks now with the key concepts of the special theory of relativity and seeing what some of those implications are for our situations, not only with traveling to stars maybe, but also combining velocities and ultimate speed limits and the like. In this video lecture, just want to say a few words about writing the speed of light in convenient units, especially when we're dealing with things like gamma. So remember, of course, gamma, 1 over the square root of 1 minus v squared over c squared, the Lorentz factor that's involved in time dilation, length contraction, and the like. And we've typically been using speed of light as 300 million meters per second or 300,000 kilometers per second. You can do it in miles per second, 186,282 actually miles per second. And if you want to be a little more precise here, it's actually 299 and some other digits there. But for our purposes, perfectly legitimate to just take 300,000 for kilometers per second or 300 million for meters per second. It's because those numbers are so big and just outside our realm of experience, sometimes it's nice just to think about the fact that it's about 1 foot per nanosecond. In other words, in a billionth of a second, light travels 1 foot, about a third of a meter. So 1 foot per billionth of a second. That's assuming it's essentially in a vacuum. If it's going through a medium, air slightly, but something like water or something like that, that's transparent, it will slow down the speed of light by the so-called index of refraction. But that's a whole other topic for a different course. So 300 million meters per second, 300,000 kilometers per second. Know what happens though if we just deal with v in terms of c. And by the way, we've been using this because I wanted you to get a feel for the magnitude of some of these numbers, or sometimes how small they are too, when we did some of the things, if you've been doing the problem sets, working with some of those numbers. But let's think about this a minute. If we would write v in terms of c, which certainly is useful if it's a high velocity near the speed of light or a substantial fraction of the speed of light. For example, v equals 0.9 c. Look what happens when we calculate gamma then. So we get gamma equals 1 over the square root of 1 minus, well, v is 0.9 c squared, so 0.9 c squared divided by c squared. Well, what's 0.9 c squared? That becomes 1 over the square root of 1 minus, on the top I've got 0.9 squared. So you remember, 9 times 9 is 81. 0.9 times 0.9 is actually 0.81. So we get 0.81 c squared on the top there, the numerator, and a c squared on the bottom. And this is where it becomes nice because, as you probably saw before I even wrote that down, we have c squareds there and they cancel. So this c squared cancels with that c squared. And I'm simply left with 1 minus 0.81. So typically when we do this, we'll just have 1 minus some decimal number, some fraction less than 1 there, and which in this case is 0.19. So you just take the square root of 0.19, 1 divided by that square root, and you've got your answer for gamma, which I think for 0.9c is what? It's about 2.3, if I remember correctly, something around there. Anyway, so makes it very easy for calculations. So often we'll have problems, or you may see problems with v as a certain percentage fraction of the speed of light. But there's another measure that's useful to know about as well that makes our life easier, especially in terms of astronomical distances, and that is the light year, which you may have heard about. So the light year is the distance light travels in 1 year. So it is a distance. It is not a time. Despite the fact we've got year in there, it's a light year. It's the distance light travels in a year. Distance light would travel in a vacuum. Distance light travels in 1 year. And it's pretty far, right? Off the top of my head, I don't have it memorized. You can actually figure it out if you know 300 million meters per second times the number of seconds in a day is, I think, 86,400. So multiply that out. Then by the number of days in a year, if you take 365 and you get the distance light travels in terms of meters per year. Divide by 1,000, you get kilometers if you want. So light year distance light travels in 1 year. And note in terms of C then what the units become. So C then it literally is just light years per year. By definition, it's the number of light years it travels in 1 year. That is C. And in these units then, it's just 1. C travels 1 light year per year by definition of light years. The distance light travels in 1 year, so it's 1 light year per year. So technically, let me just it's clear. Those are the units for C then, which equals 1. So we'll put it over here too, just to be clear. C equals 1 light year per year, and the units in general are light years per year. We'll get rid of this part there. Okay, so C is 1 light year per year, or we could have light month is the distance light travels in 1 month. So we could have C is 1 light month per month. Light day, so C is 1 light day per day. Light second is often used. In fact, 1 light second is the distance light travels in 1 second, which is still pretty far, right? It's going 300 million meters per second. So in 1 second, it's 300 million meters. Okay? So 1 light second is 300 million meters. So, but C is 1 light second per second. If you did 1 light nanosecond per nanosecond, then it's 1 foot. That's the distance light travels in 1 nanosecond, approximately. Okay? The nice thing about this, and physicists love to use units like this, because sometimes they just say we're going to set C equal to 1, because look, it just disappears in here. And the formula for gamma is just square root of 1 over the square root of 1 minus v squared. Now what we're going to do for our purposes is leave C in there, just to remind ourselves it's there, because especially when you're just sort of think about the concepts and try to get your minds around things like this, if you get too sort of simple, it's not really simple in a simplistic sense, but you're simplifying things and saying, just let C equals 1 light year per year. Sometimes you lose track of it. And so it's good to see it in the formula, but then when we actually do problems, if we use light years for a distance, then C is just 1 light year per year, and it works out very nicely that way. So that's just a few notes about convenient units for light, whether we write V in terms of 0.9 C or some fraction of C, and therefore it cancels out, or we use units of light years. And if we say, okay, our distances are going to be in light years, then our time is light years per year. The velocity is light years per year, and C is just 1 light year per year. So if you use light years, then time is going to be in years. If you use light seconds, then your time is in seconds, and so on and so forth. So long as you're consistent with that, and it's pretty easy to keep track of it, then it makes some of the quantitative analysis and calculations a little bit easier for us. In this video lecture, we want to spend a little time exploring time dilation and length contraction, which we introduced last week. And so here's the idea. We're going to do a little star tour here. Imagine a trip to a star 5 light years away. Okay, so if we could go there at the speed of light, it would take presumably 5 years to get there in a certain frame of reference, as we'll see here. So for our trip, we're going to assume that our velocity, so here's Earth, here's the star, sort of compressed together there, but the idea is that's 5 light years away. Here's, maybe it's Bob's spaceship, and traveling at velocity v, and we're going to assume v is 0.943 times the speed of light. The reason we chose that, it gives us a gamma factor of 3, so a nice even gamma factor there, Lorentz factor. So here's what we want to do, is we want to analyze the situation first from the perspective of an Earth observer watching Bob, so maybe Alice is on Earth, watching Bob travel to the star, and then analyze it from the rocket observer's perspective, frame of reference. That would be Bob in this case. So let's just think about this from somebody watching on Earth, watches Bob go by at velocity v, presumably he's had a lot of time to to get up to speed here, so he's going nice constant velocity when he goes by. We also set up here, so again, imagine for the Earth frame of reference, it's really the Earth star frame of reference because they are stationary with respect to each other. So once again, we have to imagine a lattice of clocks going all along in the Earth star direction here, and all those would be synchronized in the Earth frame. And so the idea here is that when Bob goes by Earth, we'll set it up such that the Earth clock, the clock on Earth, is time t equals 0, and Bob's clock that's going along with him is also time t equals 0 at that instant as he goes by. And all the Earth clocks are synchronized in the Earth star frame of reference, and Bob, too, has his imaginary lattice of clocks extending in both directions to infinity, and all those clocks are synchronized in his frame of reference, which, of course, in his frame of reference, he's not moving. He's stationary. And it's really the Earth and star system that is moving, and we'll get to that in a minute. But let's look at the Earth observer first and just measure, how long does it take at 0.943c, gamma factor 3, to get for Bob to get from the Earth to the star. So we have travel time here is simply going to be 5 light years, 5 Ly for light years, that's the distance from the Earth to the star, divided by the speed, which is 0.943c, 0.943 times the speed of light. And as we talked about in a previous video clip here, nice thing about using distances like light years or even light months, light seconds, although typically we use light years, especially for astronomical distances, is that the speed of light is simply 1 light year per year, almost by definition. The definition is the definition of a light year is the distance light travels in 1 year, technically in a vacuum, which of course outer space isn't quite a perfect vacuum, but pretty close to it. And so we get 1 light year per year for c. So essentially we're just doing 5 divided by 0.943 as long as we're using units of years. If we were using units of light months here, then the answer would be, we'd have 1 light month per month for c, and the answer would be in months, and so on and so forth. So as long as we keep track, hey, we're using light years here, the answer of 5 divided by 0.943 is going to be the number of years, travel time to get there. And if you do that, it comes out to be 5.30 years. Okay, and it's always good to check, does that make sense? Well, 5 light years, and it takes, you're not going quite at the speed of light, just a little less than the speed of light, so you would assume it takes a little longer than 5 years to get there, and of course that's the answer we get, 5.3. So that checks out in terms of how we think about that. Now, another thing we want to do here from the Earth observer's perspective, so that's the first thing. Second thing we want to do is, as Bob goes by here, as our rocket ship goes by, takes a photo right at that instant on the Earth star lattice of clocks. Takes a photo both of the Earth clock there and Bob's clock. They both read t equals 0. And then when Bob, the rocket, gets to the star, 5.3 years later, take another photo. And so in that photo, the star clock will read 5.3 years because this is from the Earth observer's perspective. And Bob's going along at 0.943c. And when he gets there, 5.3 years have elapsed on the Earth star system of clocks. And so the question then is, really, what does that photo show? We know the photo shows 5.3 years for the star clock. What does it show on Bob's clock as far as the Earth observer is concerned here? Well, this is where we think, okay, Bob's clock is a moving clock with respect to the Earth star system. Time dilation factor is what enters in here. So in terms of what the Earth observer sees, say Alice sees as Bob goes by, is Bob's clock runs slow compared to the Earth star system of clocks. How does it run slow? It runs slow by a factor of gamma. Remember, our basic equation is, we'll say, we've written it in different ways in terms of Alice versus Bob, moving versus rest frame. Here maybe we'll do rocket and lab frame, where the lab frame is the Earth star system. Or actually, let's just call it the Earth frame. So delta T for the rocket here is 1 over gamma. The elapsed time on the rocket is going to be 1 over gamma times the elapsed time in the Earth star frame. Okay? And gamma is 3. We set that up. So if delta t on Earth is 5.3, then the Earth observer sees, let's not use C, we try to avoid that, although we use it sometimes, observes, in this case, observes means photographs, so I might as well say observes / photographs. Rocket clock at the star, and the time on that clock is going to be the elapsed time on the Earth clock, 5.3 years, divided by 3, divided by gamma. And so that's going to be equals 5.3 years over gamma, which of course is 3 here. And if you do 5.3 divided by 3, you get 1.77 years. Of course, I've worked out the numbers beforehand, so I can't do that in my head just automatically, but just remember the numbers we're using here. So that's, in other words, when Bob gets here in his rocket ship and the photograph is taken, the star clock, which belongs to the Earth star last system, will read 5.3 years. The rocket clock will read 1.77 years. And then you're going, now, hold on a minute, wait a minute here. Now, how can that be? Because Bob is going at 0.943 c, about 0.9 times the speed of light. It's 5 light years to get there. How can it only take 1.77 years for him to travel that distance? Clearly, he would have to be going faster than the speed of light, or it would seem so. And here's where we have to remember the different frames of reference and different perspectives. So now let's take a look at what the rocket observer says, what Bob, in this case, not says, but would see, would observe as it goes along here. So, from the rocket perspective, and by the way, you may have noticed this already, this is very similar to our muon problem. In fact, really an exact analog, just another version of the muon problem. The muon problem is a version of this, although we're going to take this a little bit farther than we did with the muon problem. So, having that hint, then, think a minute, what does Bob, the rocket observer, see as he's traveling along in his frame of reference? And actually, that's a misnomer. He's not traveling along in his frame of reference. He's stationary in his frame of reference, and it's the Earth star system that's moving with respect to him. The star is rushing towards him. And therefore, here's where another aspect comes in. That's not time dilation. It's length contraction for him. He observes, let me just back up. Clearly, when he gets here at the star and the photo is taken 1.77 years on his clock, he has to agree with that. He agrees, yes, absolutely, I can see the photograph there. Clearly it says 1.77 years. Clearly I can see in the Earth observer, in the Earth frame of reference, the clock for the star is 5.3 years. And to understand that discrepancy completely, it'll take a little while here, but for the moment, there's no disagreement about the photograph here. It's not like the number is wrong. This is what's on Bob's clock. This is what's on the star clock, the Earth star system clock at that point. So now we're going to switch from the Earth frame of reference to Bob's frame of reference and say, okay, what is he observing here? And so, again, the idea is he's stationary. It's the star that's rushing towards him. And so this distance here, essentially between the Earth and star, is contracted for him because that distance is moving toward him. Imagine if you had a rod there or something, you could connect the two, right? It moves that way. That length of that rod, or just the distance, length of the distance here between the Earth and star, that's going to be contracted to Bob because that's a moving frame of reference at really negative v going in that direction to him. And so what is that distance? So the rocket observer observes that the Earth star distance is contracted. It's less than it is in its proper frame of reference, in its regular frame of reference. In other words, the proper length is shorter when it's moving. And so the proper length here in the Earth star frame of reference between the Earth and star is not 5.3, it's 5 light years. Where we put it here, up here, 5 light years. Okay? To Bob, however, the rocket observer, it's 5 light years divided by gamma. Because, again, in the moving frame here, and let's not get confused here with rocket and Earth. So I'm going to use moving and rest frame because you can switch back and forth between the frames. And in this case, for Bob, he's in the rest frame. It's Earth star system that is moving. So the length in a moving frame is 1 over gamma times the length in the rest frame when it's at rest. And so when it's at rest, it's 5 light years. But Bob sees it moving at a velocity v, 0.943 c. And therefore, if he measures that distance, he's going to get 1 over gamma times 5 light years. And gamma, we've chosen to be 3. And so he sees, so we'll call it d, the distance between the Earth and star. So we'll say DES, the distance between the Earth and star. It's not a very good D there. Sort of like a lopsided 0 or something. There we go, a little better D. Distance between Earth and star, according to, this is in the rocket frame now. The distance between the Earth and star in the Earth-star frame is just 5 light years. In the rocket frame, it is 5 light years divided by gamma, which is 3. And when you do 5 divided by 3, you get 1.67. Equals 1.67 light years. Okay? So to Bob, the rocket observer, he sees that distance as 1.67 light years. Okay? And now let's see, okay, so he's saying 1.67 light years. He's saying, I see the star rushing toward me at 0.943 c. And by the way, a question that I think has come up in the discussion forums, and a very excellent question, actually, that we never quite addressed directly is, what if velocity changes? It seems length changes, time changes. Does velocity change between frames as well? Do we have to worry about that? We'll actually be talking about that a little later this week. So we will see that the short answer is no. The velocity is the relative velocity between frames of reference, and it's going to be the same for Bob in this case, and the same for Alice, say, in the Earth-star system, the relative velocity between them. We'll see cases, though, where if, we'll do an example where Bob, say, has an escape pod, and he shoots off the escape pod from his spaceship at a certain velocity, then what velocity does Alice see that as? So we'll do examples like that. But back to our situation here, just to indicate, yes, V is going to be the same for either one of them. Bob, Alice sees Bob traveling along at V that direction. Bob sees the star moving toward him at 0.943 c as well. So from Bob's perspective then, from his frame of reference, he sees the distance that the star has to travel to get to him as 1.67 light years, because it's contracted by the factor of gamma. And how long does the star travel toward him until it reaches him? Well, it's the time on his clock, 1.77 years. We know that the star and Bob, the rocket, are in the same place when Bob's clock reads 1.77 years. And so what does that mean here? Does this connect with that? So let's think about this a minute. Distance the star has to travel to get to Bob, according to Bob, is 1.67 light years. It's traveling at 0.943 c to him. So let's do that calculation. Let's just say that time for star to reach Bob, we'll say. So Bob is in the rocket. Time for the star to reach Bob is simply the distance divided by the speed, equals 1.67 light years. 1.67 light years divided by 0.943 c. That's how fast the star is moving toward Bob and his rocket. And again, we're doing c is 1 light year per year. So 1.67 divided by 0.943, the answer is going to be in light years. Do you know what you get? If you do it, you get 1.77 years. In other words, it's all consistent. Okay? So that from Bob's perspective, he sees the star rushing toward him at 0.943c. He sees the distance the star has to travel as 1.67 light years. And he sees his clock tick for 1.77 years when the star reaches him. And the photo is taken at that point. And his clock says 1.77 years. Meanwhile, of course, from Alice's perspective on Earth, she sees Bob traveling toward the star at 0.943c. In her frame of reference, that distance is 5 light years. Therefore, it takes Bob 5.3 years. So when he gets to the star, on the Earth star clocks, Alice's lattice of clocks there, it'll read 5.3 years. And Alice observes Bob's clock, though, running slow by the time dilation factor, and therefore observes Bob's clock to be 1.77 years. Okay? So in that sense, Alice says, it makes sense to me. This certainly makes sense to Alice. And she says, Bob, your clock is running slow. I don't know what the problem is over there, but I get it as 1.77 years. Meanwhile, Bob says, well, I don't know about this 5 light year distance you've measured, because to me it's clearly 1.67 light years when I measure that distance. But you are right, it takes me, because it's a shorter distance in my perspective. Obviously your measuring system is messed up, it looks like. But for 1.67 light years, at the speed the star is coming toward me, 0.943c, it takes me 1.77 years. And therefore, at least they both agree that the 1.77 years is correct, although for different reasons there. Because Alice is saying, hey, your clock is running too slowly. And Bob is saying, no, it's not my clock that's running too slowly. It's your distance measurement that is messed up. But they both agree on the 1.77 years. It's a little more difficult, though, and this is what we're going to be heading toward this week to a certain extent, to explain how does Bob explain this 5.3 years factor here. So that's something we're going to have to do. But there's another thing here, too. You say, okay, I sort of see how it hangs together. There seem to be some loose ends we're going to have to worry about. It's one of those things you have to just ponder as well and let it sink in for a while. And sometimes it just takes a while. I've been in classes before where it didn't really sink in until after the class was done, unfortunately. But sometimes that's the way it is. But let's think about something here. Okay, let's go back to Bob's frame of reference, and he's observing Alice's lattice of clocks, the Earth star lattice of clocks. You can imagine a whole bunch of them there, all synchronized for Alice. But as Bob is observing that lattice of clocks go by, let's think about this a minute. Doesn't time dilation work in that direction as well? And the answer is yes. Works both ways. And so if Bob is seeing the elapsed time for the star to get to him is 1.77 years, how much elapsed time does he see pass on the Earth star clocks? Well, time dilation applies. This exact same relationship applies here, except let's make it a little more general here from what we had before. So it's delta t moving. Okay? In other words, I'm observing a clock in a moving frame of reference. Okay? And this is rest. So if I'm at rest, I'm observing my clock in my frame of reference, and then I observe a moving clock, that moving clock is going to run slow by the factor of gamma. So Bob, in his frame of reference, has his clock there in the cockpit with him. He's observing Alice's clocks rush by him in the Earth star system as the star comes towards him. Therefore, he will see those clocks running slowly by a factor of gamma. And so when he sees, on his clocks ticking away nicely, 1.77 years, how much elapsed time will he see on Alice's clocks? And the answer is, we're going to have room over there, so we'll squeeze it in right here, say. Okay? So this is Bob's observation. Sorry, squeeze that in there. So that's observation of, we'll say Alice's. Okay, just remember Alice here. So here's Alice. Get her up here. Here's Bob. B for Bob. Bob's observation of Alice's elapsed time. Okay, according to her clocks. It's going to be 1.77 years, because he's got his clock right there. It's ticking away nicely. When the star reaches him, yes, it's at they take the photograph, it's at 1.77 years. Her clock's at 5.3 years, but we're not going to worry about that for the moment. She thinks it's correct. He has other ideas about that. But what is the elapsed time from Earth to the star, or really the star getting to Bob here, that Bob sees on Alice's clocks? And it's 1.77, because that's the time on his clock. So it's 1.77 years divided by the gamma factor. It's always 1 over gamma here in this case, when we're going in that direction. So that's divided by gamma, which is 3. And the answer you get if you do that is, I think, 0.59 years. And now you really go, huh? Right? How can this make sense? You know, we can sort of see, yeah, okay, I get time dilation. Alice will observe Bob's clock's running more slowly, and so 5.3 years gets 1.77 years, and sort of get Bob over here, the rock observer, the distance is contracted, right? And therefore, shorter distance, and therefore his clock will run for 1.77 years, okay? That. But then Bob, looking at Alice's clocks running slowly, just as Alice sees Bob's clocks running slowly, Bob is seeing Alice's clocks running slowly. By the factor of gamma, you get his elapsed time divided by gamma is 0.59 years. How in the world does, you've got 5.3 years. Isn't that the elapsed time on Alice's clocks? That's the elapsed time she's getting. How is Bob getting a value of 0.59 years for the elapsed time on Alice's clocks? And to understand this quantitatively, we're going to have to do some work this week. We're going to develop something called the Lorentz transformation, because that's going to help us understand this. Among many other things, it's useful for much more than just that. So it's going to help us understand this. But I'll give you a hint on it. And that is, when you're thinking about the special theory of relativity, you can't just focus on time dilation. As we've seen here, time dilation and length contraction go together in the analysis, often from different frames of reference. In one case, you're using time dilation. From the other perspective, it's length contraction that is the issue. But there's a third thing here, too, that we cannot forget, and that is the relativity of simultaneity. That clocks synchronized in one frame of reference, are not synchronized in the other frame of reference, moving at a velocity via an inertial frame of reference. And that is the key to understanding this. And earlier on in the course, qualitatively, we talked about how leading clocks lag. That if you have two clocks, say, or a series of clocks moving past you at, obviously for this to really be observed, it has to be a pretty high velocity, but in principle it's for any velocity. As it's moving past you, if you're observing those clocks go by, the clock in front is going to lag the clock behind. The clock behind will be ahead of, time-wise, the clock in front. And that is the key to understanding this discrepancy here. And we want to be able to understand it quantitatively. We want to be able to show that add the numbers together in some way, and yes, you actually do get the 5.3 years back in. So to do that, we have some work to do this week, but this is, again, exploring time dilation and length contraction. Originally, I thought I would do this in a couple weeks when we talked about like the twin paradox, but I decided it was good to introduce it this week to try to mull over a little bit how time dilation and length contraction works, and also the relativity of simultaneity. So that's where we're heading over the next few video lectures, to do the Lorentz contraction and then do leading clock's lag in a quantitative sense, as well as looking at some aspects of velocity and so on and so forth.